The cheapest battery on Earth is not made of lithium. It does not contain cobalt, nickel, or rare earth metals. It does not require a clean room, a chemical engineer, or a billion-dollar gigafactory. The cheapest battery on Earth is a stack of ordinary firebricks, the same kind of clay and iron oxide blocks that have lined pottery kilns and pizza ovens for 2,000 years. Heat those bricks to 1,500 degrees Celsius using simple electrical resistance wire, wrap them in ceramic insulation, and you have a thermal battery that can hold energy for weeks. The materials cost roughly $50 in raw form. The technology cannot explode, cannot leak, and cannot catch fire. And yet, in the United States of America, in the year 2026, you cannot legally install one in your basement. Tonight, we examine why. To understand what a thermal battery actually is, you have to abandon everything you think you know about how electricity is stored. There is no electrochemistry happening inside these systems. There are no ions migrating across membranes, no electrolytes degrading, no dendrites growing in the dark. A firebrick thermal battery is, in the most literal sense, a giant industrial toaster. Electricity flows through nichrome resistance wire threaded through a stack of refractory bricks. The bricks heat up. They keep heating up until they are glowing white hot, somewhere between 1,100 and 1,800 degrees Celsius. The energy is now stored as raw heat, locked inside the dense ceramic mass. When you want it back, you blow air through narrow channels in the brick stack. Out the other side comes superheated air, which can drive a steam turbine, feed an industrial process, or warm a building for days. The materials list is almost insulting in its simplicity. Clay, iron oxide, nichrome wire, ceramic insulation. These are not exotic substances controlled by foreign cartels. They are not flammable. They cannot poison groundwater. They cannot enter thermal runaway and burn a warehouse to the ground the way a lithium-ion battery can. The worst-case failure mode of a brick thermal battery is that it cools down faster than expected. And yet the cost story is what should stop you in your tracks. Lithium-ion utility scale storage runs between $200 and $400 per kilowatt-hour installed. Brick thermal storage media, the raw bricks themselves, can be sourced for as little as 30 to 50 cents per kilowatt-hour. Even when you build out a full commercial thermal system with controls, insulation, and heat exchangers, the all-in cost pencils out around $10 per kilowatt-hour. That is roughly 10 times cheaper per unit of energy stored. Across the trillions of dollars projected for the global energy transition, that cost gap is not an academic curiosity. It is a strategic threat to several extremely wealthy industries. The retention story is just as remarkable. With proper ceramic insulation borrowed directly from blast furnace and steel mill engineering, heat loss can be held below 1% per day. Read that again. 1% per day. A heavily insulated brick stack does not just bridge an overnight gap the way a home battery does. It can bridge a cloudy week. It can hold the energy from a sunny October afternoon and release it on a gray November morning. In October of 2025, Rondo Energy commissioned an industrial unit holding 100 megawatt-hours of thermal energy, delivering continuous heat to a factory between solar charging cycles. That is not a laboratory demonstration. That is a commercial deployment, operating today, paying for itself in dollars and tons of avoided gas. The science behind all of this is not new. The principle dates back to the Bronze Age, when human beings discovered that thick stone hearths kept giving off heat long after the fire died down. European homes in the 1800s used night storage heaters with virtually identical physics, charging on cheap overnight electricity and releasing the warmth all day. What is new is the pairing of this ancient idea with cheap solar power and the academic rigor of 21st century materials engineering. The modern terminology came from MIT researcher Charles Forsberg, who coined the acronym FIRES, standing for Firebrick Resistance Heated Energy Storage. Forsberg argued that fires could put a floor under wholesale electricity prices by soaking up surplus solar and wind generation that would otherwise be curtailed. Stanford professor Mark Z. Jacobson then ran the numbers across 149 countries. His modeling concluded that firebrick storage could save $1.27 trillion in capital costs across the global energy transition. It could reduce required battery capacity by roughly 14.5% and trim projected hydrogen demand by approximately 31%. Those numbers are not marketing copy. They are peer-reviewed. A startup called Electrified Thermal Solutions has taken the engineering one step further. Their innovation is an electrically conductive firebrick, which means the brick itself acts as the heating element. There is no separate resistance wire running through the stack. You apply a voltage across the bricks, and the bricks heat themselves. It is a beautifully simple piece of materials science that eliminates one of the few remaining failure modes in the technology. None of this is exotic. None of this requires breakthrough physics. The technology never failed. It was simply forgotten during the era of cheap natural gas, when no one needed to think very hard about how to store renewable electricity, because there was no renewable electricity to store. So why can you not buy one for your house? The answer is not that it has been outlawed. There is no statute on the books in any American state explicitly banning brick thermal batteries from residential use. The barrier is something more insidious and harder to fight. It is regulatory friction. There is no UL 9540 safety listing for residential thermal storage. Without that listing, no installer in the country can pull a permit. Building codes like NFPA 8.5 and the International Fire Code, Chapter 12, were written specifically around chemical battery hazards, thermal runaway, flammable electrolytes, and toxic off-gassing. A firebrick stack does none of those things, but the codes do not know how to classify it. The technology falls into a regulatory gray zone with no clear compliance pathway. Even if you could get a permit, utility tariff design rarely credits off-peak charging for thermal systems the way it credits chemical batteries. Without the right rate structure, the homeowner economics collapse before they begin. Then there is the insurance problem. It functions as a hidden second lock on the door. Insurers have no actuarial data on residential units that store energy at 1500 degrees Celsius. Without historical loss data, no underwriting model can be built. Without an underwriting model, no policy gets written. Without an insurance policy, no permit gets issued, even in jurisdictions where the building code would technically allow installation. It is a perfect chicken and egg loop that stalls the entire residential market before any product can reach a customer. Behind the regulatory thicket sits a much more financial story. Industrial process heat is the single largest market for natural gas in the United States. Heating cement kilns, steel furnaces, food processing boilers, and chemical reactors consumes more gas than every American household combined. Thermal batteries are not a marginal threat to that market. They are a direct substitute. A brick stack charged by solar power produces the same superheated air or steam that a gas-fired boiler produces, at a fraction of the operating cost and with none of the carbon emissions. Gas distribution companies understand this. Their lobbying budgets against industrial electrification mandates dwarf the entire thermal storage startup sector by orders of magnitude. This is not a conspiracy theory. It is publicly filed lobbying disclosure. And yet, on the industrial side of the fence line, the technology is already winning. Rondo Energy powers California food processing plants today, replacing gas boilers with brick stacks charged by surplus solar. Antora Energy uses glowing blocks of solid carbon to do the same thing at even higher temperatures. Electrified Thermal Solutions is operating commercial pilots throughout 2025. These companies have figured out that the fastest path to market is to bypass residential code entirely by operating inside industrial zones, where building codes are different, insurance is bespoke, and customers care about economics rather than regulatory inertia. The fence line of the factory is where the technology is proving itself. The real story here is not a conspiracy. It is bureaucratic lag. Codes written around one technology cannot accommodate a fundamentally different technology quickly. Incumbents have no incentive to push for updated standards that would erode their market share. The standards writing committees at NFPA and UL are dominated by representatives from the HVAC industry and the chemical battery industry, both of whom benefit from the status quo. Underwriters. Laboratories moves on industrial timescales, not innovation timescales. Code updates typically lag commercial deployment by 5 to 10 years. None of this requires malice. It only requires inertia, and inertia is plentiful. The geographic pattern of adoption is itself revealing. European industrial customers are moving on thermal batteries faster than their American counterparts, partly because their gas utilities have less regulatory capture, and partly because their carbon pricing makes the economics even more obvious. Asian manufacturers see thermal storage as a critical companion technology for their massive investments in solar manufacturing. The political economy of energy storage is on full display in the global map of who is deploying and who is hesitating. What happens next is in committee review, quite literally. A UL listing for thermal storage is making its way through the standards process. Once it lands, the residential market will unlock in stages. First, in unregulated rural areas where building inspectors are scarce, then in early adopter green building markets, then in mainstream new construction. The industrial fence line is where the technology will continue to mature in the meantime, with each Rondo unit and each Antora pilot building the operational track record that insurance underwriters need to write a policy. Hobbyists are already building small-scale demonstrations in their garages with bricks, nichrome wire, and ceramic blanket insulation, assembled for around $50 in raw materials. The physics works on a kitchen counter the same way it works in a megawatt-scale industrial unit. So we return to the question we began with. The cheapest battery on Earth is not banned in your home. It is, instead, stranded outside the door by a thicket of codes, listings, tariffs, and underwriting forms that were written before the technology existed. The question is no longer whether the bricks can hold heat for weeks. That is settled science, demonstrated in California factories operating today. The question is whether regulators, insurers, and standards bodies will allow this ancient principle to leave the industrial fence line and walk into the basement of an ordinary American home. The physics will keep working while the paperwork catches up. Whether you live long enough to see it warm your house is a question not of engineering, but of bureaucratic timelines, and those timelines have always moved more slowly than the people waiting on them would prefer.